So I still have some things to say about the constraint forces, especially as it relates to non-holonomic constraints. And we'll see some examples, actually some vehicles and kids' toys that I'll show. But first, I wanted to talk about, in very broad strokes, where do the Lagrange multipliers come from? And so we write the constraints. Constraints in the, we'll say the linear non-holonomic form. This is what we ended with last time. If you have both kinds of constraints, you write all of them in this linear non-holonomic form, or it's also called the Pfaffian form, after Pfaff. And this was where you write, things are linear in the Qi dots, and they have coefficients that we write as ALI, which could be functions of Q. So we're summing over the generalized coordinates. And instead of writing this as Qi dot, I'm just going to go ahead and say it's dQi dt. And then we have this other term that's sometimes written as ALT, could be a function of Q. It just doesn't multiply the one of the generalized velocities. And L, this index L is the index of the constraint. L goes from 1 to capital S, the number of constraints, total constraints. So if we've got our constraints written this way, then multiply by dt. And I just get the same thing, but this is ALI Q dQ plus ALT Q. And now there's a dt over on this term. So I've got that for each of my constraints. And now I replace the dQs with delta Qs, and I'm treating these as instantaneous virtual displacements. So replace the dQi with delta Qi. And remember, this idea of instantaneous virtual displacements is sort of a mathematical tool we use to get at the equations of motion. It was a fundamental part of D'Alembert's principle. And I may not have said it then, but they are considered instantaneous. And it's important that they're instantaneous. Instantaneous means that dt equals 0. So this part of the constraint won't play an important role, at least in what we'll do next. So we've got constraints that look like this, delta Qi equals 0. And there's, L goes from 1 to S. So these are the constraints written in terms of virtual displacements of the generalized coordinates. So written in terms virtual displacements of the Qs. So we've got S of these equations, and they are satisfied if the delta Qs satisfy the satisfy the constraints. So we are going to assume that we can satisfy the constraints. So that means this equation is true. We've got some sum over the delta q's equals 0. We could multiply that by anything, and it's still true. So we're going to multiply this by some scalar quantity. So we multiply each of these by some scalar quantity. It might be a function of things, but we'll call that scalar quantity lambda L, right? Because there'll be an index L attached to each of these. So that means we've got lambda L multiplied by this sum. And this is still, so we still have, there's an index L that goes from 1 to S. So we've got S of these equations. We've just introduced some lambda L. The lambda L's are undetermined, at least yet. They're undetermined at this point. They become something that is solved for. And they're called, we introduce one for each constraint. So this index L goes from 1 to S, and they are called Lagrange multipliers. So we've introduced a Lagrange multiplier lambda L for each constraint. That's okay. We can do that. So we have a system of equations that are still true. We've got these lambda L's. We don't know what they are, but we're going to sum over these S equations, which we are free to do. And if we sum over them, that's a summation that still equals 0 because we're summing over things that equal 0. So we're going to sum over the S equations. So here we go. And now the index of summation is L. L goes from 1 to S of lambda L. Let's write it this way. I goes from 1 to N. ALI. Oh, I put an N here. That's a Q. ALI, function of Q. Delta Q equals 0. Delta QI. So this is a double sum. I can switch the order of the sum. And I'll tell you why once we do it. So we switch the order of the sum. So we've got a sum. I goes from 1 to N, and then L goes from 1 to S of lambda L, ALI, delta QI equals 0. So now I've got some giant summation thing that equals 0, and there's delta Q's involved. I can even put, maybe I'll put parentheses around here so you can kind of see what this looks like. This is similar to how I wrote D'Alembert's principle. D'Alembert's principle was a sum from 1 to N of some stuff times delta Q i's equals 0. And a few lectures ago, we wrote this, and then we said there's two different cases. There's the case where you don't have any constraints on your generalized coordinates, meaning your generalized coordinates are free to vary independently, and that led to a certain equation of motion. Now that we have constraints on our Q's, which is sometimes unavoidable, if we have constraints on our Q's, we can't just vary these delta Q's independently until we do this trick. And the trick is that we subtract this double sum here from D'Alembert's principle. So if you remember D'Alembert's principle, so we subtract this. I think it's just a convention that it gets subtracted. You could add it. That would just change the interpretation of what the Lagrange multiplier sign is. So we subtract this from D'Alembert's principle, which, if you remember, was this sum over the generalized coordinates. I'll write this in square brackets. D by dt partial L partial Qi dot minus partial L partial Qi minus Qi. And so this is writing it in the full way that we've developed. That would be, this would be, times the delta, I'll write these in blue now, delta Qi equals 0. So now that we've subtracted this double sum here, we've got now a sum. L equals 1 to S of lambda L, write this in red, lambda L ALI, which is possibly a function of the Q's. Maybe make that red too. Okay. So now we've got this, okay, where the Lagrangian is the kinetic minus potential energy, and it's unconstrained. That means we haven't yet imposed any, in writing the Lagrangian, we don't impose the constraints. We're using the Lagrange multipliers to impose the constraints. So this is the unconstrained Lagrangian. So this is just full dependence on the Q's, Q dots, without imposing constraints. I think I wrote dependence all messed up. It's all right. Okay. So the trick is, and you could read more about it elsewhere because it's tricky. We can choose the lambda L's so that the delta Q's, so each of these delta Qi's can vary independently. And that's important so that they could both vary independently and satisfy the constraints. So that means we've got this sum, right? Just like before, got a sum from 1 to n of these bracketed terms times the delta Qi's equals 0. So that means if the delta Qi's can all vary independently, the only way this equation can be true is if everything in the square brackets is also 0. Okay. And so what does that mean? That means, so take this square bracket term, and then we'll just write it in the usual way we've written our Lagrange's equations, where we've got the dependence on the Lagrangian on the left-hand side. And then this equals Qi and C plus this sum of over the constraints. L goes from 1 to S, lambda L ALI, which could be a function of Q's. I mean, we could just drop that. Okay, so now we've got, there are, the index I goes from 1 to n of these. So this is what we have for Lagrange's equations when there are constraints on the Q's. And last time we said, okay, what is this? I used the notation capital CI. This is the generalized force of constraint. And if you're wondering where this is, I think you can see this in 2 different places in the Kasdan and Paley book. This is chapter 13. I think this is somewhere near equation 13.29. And in the Greenwood book, which goes into more detail, this is in chapter 2, somewhere near equation 2.52. Okay. Now, so this allows you to, you're solving for what we said last time. You've got these n equations and then the s constraint equations, and then you have n plus s unknowns, which you could think of as q1 through qn double dot, and then lambda 1 through lambda s, the Lagrange multipliers. So you've got n plus s equations and n plus s unknowns. There's also something to note, which is that these generalized forces of constraint can be related to Newtonian forces and moments in the, let's say, usual way. So let me write this. Oops, CIs are related to forces and moments of constraint in the way that we would expect. So let me write CI. This is going to be a sum over, and I'm assuming the case where we have capital N, possibly rigid bodies. If they're rigid bodies, then you have moments and stuff. If they're not rigid bodies, then all you have is forces. So this is going to be a sum over forces, Fj, and I'll write up here constraint, dotted with those gamma ji's, those projection vectors, or projection vectors, plus and moment of constraint, dotted with beta ji, which are also projection vectors. So this is the same form as you would write the non-conservative forces, but instead of Fj constraint, it'd be Fj non-conservative applied force. These are forces that maintain constraints. And we've shown this before, but what are these projection vectors? Just to remind us, this is the partial derivative of the inertial velocity of the jth particle, dotted with qi dot, and beta ji is partial omega j. So the angular velocity of the jth body, partial qi dot. So you can, I mean, often you might not, to solve for your system, you might not need to know what the forces of constraint and moments of constraint are. All you need to know is those Lagrange multipliers, but sometimes you do want to know what these forces and moments of constraint are. So we're going to look at some systems where we try to figure that out. I'll do one that you're probably growing tired of, but that's okay. Let's do an example. This is the baton with the wheel under it. or it's kind of like a stick figure shopping cart. Where's my, there it is. Yay. Okay, so we got this situation. And suppose you want to know what the force of constraint is for this. For the wheel. I mean, by wheel, we mean sort of what's keeping this particle one. It should be sliding freely, but because we put that kind of skate thing under it, it can only move along the axis of the baton. It cannot move laterally. So if we were to write that that normal direction that we've shown before, there's no motion in that direction. So there has to be a force that's keeping that happening. So we've written it a few times before, but we'll write the, how did we write? We wrote the constraint in such a way that we had, I'll write it this way. The constraint for the wheel, we also called that a knife edge constraint. It had A1, I'll write it as A1x. So the coefficient of x dot is negative sine theta. The coefficient of y dot was cosine theta. And the coefficient of theta dot was 0. And there was nothing else. So if we were to write the x Lagrange equation, what would we have? D by dt L partial x dot minus partial L partial x equals, and there's no non-conservative force. So all there is the force of constraint on the right-hand side here. And there's only one constraint. We're considering A1x. So this means, sorry, lambda 1. So lambda 1 times negative sine theta. So this is negative lambda 1 sine theta. Lambda 1 is currently unknown, but right, this we have also called it's the generalized force of constraint. I guess we can call it CX if we want, but let's just call it C1. I'm ordering things as Q1 equals X, Q2 equals Y, Q3 equals theta. So we've got 3 degrees of freedom here. So C1, and we're only dealing with particles. We have 2 particles, no rigid bodies. So using the formula above for what the generalized constraint force is, this is a sum from 1 to 2, or the 2 bodies here. The force of constraint on each of these, dotted with gamma J1. And we've done, I don't know if we've got these gamma J's before. So gamma 1, 1. This is partial V1 partial X dot. And that ends up being, because this velocity, right, if you write the unconstrained velocity is X dot in the, let's give some directions here. This is N1, N2. So this is X dot N1 plus Y dot N2. So partial V1, the unconstrained velocity, partial x dot gives us n1. Gamma 2, 1 is, oh, sorry, gamma, I'll just write as an example, gamma is particle 1 and 2, partial v1, partial y dot is n2, etc. to get the others. If you're to work out what this constraint force is, what you end up with is that you get the force of constraint on particle 1 dotted with n1, which basically means the force of constraint on particle 1, the x component, so we could write it that way. So there's some unknown force of constraint. I don't know what color to make it. I'll make it orange. So there's a force of constraint here. Oops. It makes sense that there'd be something there. So there's a force of constraint, and it's got an x component and a y component. And from this, we could figure out what the y component is, because this and this are equal. So the x component is lambda, I'll write it this way, lambda 1 minus sine theta. And similarly, from the y Lagrange equation, if you were to work that out, you get that f1, the constraint, the y component equals lambda 1 times cosine theta. Remember what the n direction is up here? You might not. That's okay. The n direction, that normal direction, is minus sine theta cosine theta. So it's looking like the force of constraint equals lambda 1 times the n hat direction. And that's how I drew it up here. So the force of constraint is in the same direction as the normal to the skate. So the direction in which that particle is not allowed to move. That makes sense. You could also further work out, because you could take the magnitude of the force of constraint. This normal direction has magnitude 1, so this has magnitude of lambda 1. And from the Lagrange's equations, you could work out that that'll give you that lambda 1 is minus ml theta double dot, which does have units of force. Mass length divided by time squared. So that's good. It has units of force. So if we were to sketch just a little picture of our system, right? We've got this normal force. We've got, this is theta. Now imagine that this thing it has an angular acceleration in that direction. So we've got theta double dot moving that way, then this, let me write this force of constraint just generally. The force of constraint is minus ml theta double dot and in the n direction, n hat. All right, that is red. So the force of constraint would actually be going the opposite direction here. So that means the actual force of constraint would be keeping this that way. Because it would, it just is. So you could work out what forces of constraint are through the Lagrange multiplier method. It's sometimes cumbersome, but it's doable. And it could be automated, right? We do things by hand just to give you the idea, but if you were working on a complicated system, you would want to do this differently. You'd want to automate this using your own code or use Mathematica. Here's a more complicated system. And so some mechanicians in the 80s got inspired by, there was a kid's toy, and there's this really awful commercial from like 1984 that you could look up. I won't show you the commercial because it's pretty bad. But where is it? The first devices, they were called the roller racer because, and they kept saying in the commercial, like, how does it go? How does it go? It's this interesting little thing where you could, where the center of mass is, you're basically sitting there, and even though there's two wheels, right, there's two wheels over here, you could treat them like it's just one constraint. You have a knife edge constraint right there, which means there's there's no motion in this normal direction. So to a good approximation, the two wheels can be treated as just one knife edge constraint. And we'll say that, you know, right here, this is the kind of point that we're tracking. So the velocity of that will be x, be some unconstrained velocity of the center of mass there. Let's call this point C. We'll call this point B up here. This is where there's another set of wheels. There's a pivot point in between them, but the non-holonomic constraints or knife edge constraints due to the wheels are as such. We'll call, since this angle has an angle psi up here, we'll call this in red, this is E psi. It's a unit vector that increases in the direction that psi is increasing. It's called the roller racer, and there's other variations on it. There's one called the easy roller. There's another one called the Twistcar. So people have taken this idea and done some other things with it. There's two non-holonomic constraints. The first is that VC dotted with E theta is 0. And the second one is that the unconstrained velocity of point B dotted with E psi is 0. The generalized coordinates are x, y, theta, and psi. So that means there's a velocity space. Remember our discussion of velocity space, x dot, y dot. theta dot psi dot. So at each motion in time, each of these constraints in this 4-dimensional velocity space, it says at each point in that velocity space, each constraint says there's a 3-dimensional hyperplane in which you can locally move. And because there's 2 constraints, you have to look at where the 2 hyperplanes. It's not easy for me to sketch 4-dimensional space, right? I can't do that. So this is just sort of giving you an idea. So let's say at this point, there is locally a plane that corresponds to one of the constraints. And then there is another plane, and they might intersect in some kind of interesting way. And so you can only move along that intersection. The intersection will actually be 2-dimensional. Here I've drawn it as just one line. So there's all kinds of things, interesting geometry related to this. Typically, the way it's controlled is that you directly control this phi or psi angle. So there's usually a steering wheel attached to the pivot, and you're able to change this psi angle. So it's an interesting control problem because there's one control input, and it's direct control of psi. But then there are 4 generalized coordinates, right? X, Y, theta, and psi. So if you remember what I mentioned last time is this question of accessibility. Can I steer this thing so that I can reach any XY point and any theta and any psi? I don't know. But you might be wondering, like, how is there only one? Why are you not? Where's the no thrust or something? By just changing this control input in some periodic manner, you actually make this thing move. And it's surprising. So here is, I don't know if you could see this. It says, just as the kid twists the steering wheel, what will happen? This is one variation on that theme. You see the wheels behind, and you see the kid with the steering wheel, that's the pivot. And it might be hard to see, but the other 2 wheels are a little bit offset. They're actually behind the pivot. In the sketch, I showed them in front of the pivot, but these are behind the pivot. As he turns the steering wheel, he'll actually move forward through some strange undulation. It's kind of like when you're skating and you kind of push off. Yeah, I think it is called a plasma car as well. So we got one of these because, of course, we get one of these. I might be a little bit too big for it. But so this is my my older son when he was like 2 or 3. And here he is driving around, and we had a strobe light on. You can't hear the music, but it's pretty awesome. So non-holonomic mechanics is so simple, a 2-year-old can do it. There you go, super fun. You could even make a robotic version. I don't know where I got this, but somebody made a robotic version. So there's these 2 wheels in the back, which are just skates. They're just moving passively. The only thing that's happening is a pivot in the front is moving. I think we got to take this back to the beginning. So this pivot oscillates back and forth, and you get locomotion. This thing can actually turn and do some cool stuff. There's another version of this, and it's called the easy roller. So you could sit in it, and then you use your feet instead of your arms. Use your feet in this front thing that looks like handles, but you use your feet to push it back and forth. And I learned about that because I had a former student who was visiting Ecuador, and he saw this girl.
Bottom line, that's, you know,
and so he thought, oh, Dr. Ross is going to love this.
Have you seen this Brazilian
dance?
dance?
I had never seen one, and so I had to go out and get one.
The limbo? She went down and down, and
yeah. So, do I have any other cool things? No. So If we were meeting in class, I would bring these and you could try them out. So sorry. Actually, maybe I could bring them somewhere. You could try them out. I don't know. Anyway. And you get exercise too. So it's not bad. It's a good thing. I probably won't assign this thing as a homework problem. It's kind of complicated. But if you do have a chance, look up the silly 1980s commercial about it, because their catchphrase in the 80s, it was all about catchphrases. They would say, "How does it go? How does it go?" And it's not easy to describe how it goes. It's something related to non-holonomic mechanics. People didn't even know how a bicycle balanced. They thought it had something to do with the gyroscopic effect of the wheel, but then they designed one that did not. And since I did mention bicycles, now I have to show you one. You might think that you're the one that stabilizes a bicycle, but this is a video taken by a group in Cornell. So they take a bicycle, and you see how it's stable without anybody on it? So some bicycles are just self-stabilizing once they reach a certain speed, and it's so stable, when he gives it a shove, it's still stable. And that is pretty remarkable, because we didn't know until a few years ago that there certain effects were not involved. Like, it has nothing to do with the gyroscopic effect. You can create bicycles that do not have a gyroscopic effect of the wheels, and they're still self-balancing. So it has something to do with non-holonomic mechanics. And kind of complicated. All right, let's look at another example. Here's another example for like solving forces. This is a disk or other thing. Disk, cylinder, maybe a ball rolling downhill. And we might get a chance for you to see this. So I have a platform, and I have this is like a very heavy metal thing. And okay, it rolls. So what are the forces of constraint on it? Well, let's do a little sketch. So here's my sketch. We've got a, we'll say that we're rolling downhill with this angle is alpha. Here's a cross section of the cylinder or the disk. This is something with mass m. It's got a radius, I don't know, r. Here's the center of mass, g. And right, if we were to track, here's the point of contact. If you were to track, and then I'll draw, that's the point of contact, and then also here's this dashed line is just the vertical. If I were to track this angle theta, right? Think about what's happening. Theta, so I've drawn some other kind of purple notch, purple line on here, right? And that the angle from the orange to the purple line is going to increase as this rolls downhill. So theta will increase. I guess, of course, I've got gravity affecting things. I'll choose some point up here and track the distance that I've moved along. This is S. So S is the distance from the top of the ramp And theta is just an angular variable that tracks how this rotates. So I've got, it's a 2D rigid body system. I guess I could also say that this ramp has a certain length. It's got a length L. So let's find the equations of motion. We want to both find the equations of motion and the forces, and because it's a rigid body, moments of constraint, just so that we get some practice doing that. So the constraint is, what is the constraint? The constraint here is it's rolling without slipping. So for this problem, I'll just sketch it again down here, a different sketch. I'll make the, whoops, I don't want to zoom in there. I'm gonna write a frame, an inertial frame, where one of the directions is parallel to the ramp. So I'll call that the E1 direction. And then normal to the ramp is E2. And so this disk, right, as it's rolling, this angle theta will be increasing and S will be increasing. So it'll be S dot. So if I were to write this as a velocity, the velocity of the translational velocity is going to be S dot in the E1 direction. What about the angular velocity? So if I've written E1 that way and E2 the other way, then I need to get an E3 to have a triad. E1, E2, E3 is actually coming out of the screen. The way that this is rolling, it's rolling with an angular velocity that has a rate of theta dot, but what is the axis? So as theta dot is increasing, I use the right-hand rule, as theta dot is increasing, the way that I've drawn it here, my thumb is pointing into the screen. So that means this is in the negative E3 direction. So I've got the translational velocity and angular velocity, okay? I'm going to need those projection vectors. Remember those gammas or betas from above? So if I write, I'll write partial V, partial S dot. That's E1. And if I do partial V, partial theta dot, well, that doesn't depend on theta, so 0. Okay, those are the gamma vectors. What about the beta vectors? Partial omega, partial S dot. Well, it doesn't depend on S dot. What about partial omega, partial theta dot? Well, negative E3. Okay, so now I have what I need to write at least the generalized forces and moments of constraint that would show up in my Lagrange's equation. Let's see, am I forgetting something here? I'm moving papers all around. I got anything there? No, okay, good. All right, so the generalized forces of constraint. Right, I would have I've got two generalized coordinates, S and theta, so n equals 2. CS, there'll be a generalized force of constraint in the S direction. So I'm just sort of, you know, treating, this is Q1 and then this is Q2, but in form, this, you were writing this in the index notation, you call it C1, but let's just call it CS. CS is, I only have one body here, so I don't have to sum over any bodies because there's just one. I'll write force of constraint, whatever it is, dotted with partial V partial S dot, plus, and now a moment of constraint, dotted with partial omega partial S dot. Okay, but partial omega partial S dot is 0. Partial V partial S dot is E1. So my force of the generalized force of constraint is in for CS is in the E1 direction. Okay. What about C theta, which also would be called C2? C sub theta, again, force of constraint, now dotted with partial B partial theta dot, plus the moment of constraint, partial omega partial theta dot. Okay, partial V partial theta dot is 0. And over here, this is in the negative E3 direction. Okay. So if we compare these equations, then what do we get? We can conclude that the force that what the force and the moment of constraint are. We can conclude that the force of constraint equals where is my equations 1 and 2? I think I may have skipped something, so hold on. We may need to write Lagrange's equations. Yeah, hold on. So back up there. We have to write the Lagrange's equations. So what is the Lagrangian? So L we'll write as T minus U. Okay. The U is due to gravity, and U is from gravity. If we look at our diagram up here in the upper left, it's mg times the height. So this is mg L minus S sine alpha, which is mg. We'll write it in terms of things that depend on our generalized coordinates and those that don't. So we have negative mg S sine alpha, and then we have this other term, mgl sine alpha. This doesn't depend on any generalized coordinates, so we can ignore it. We don't need to carry it around. This thing depends on a generalized coordinate S, so it will actually make a difference when you take any partial derivatives. Yeah, why are we ignoring this? If you take partial derivatives of it with respect to S or theta, you'll just get 0. So you can safely ignore it and not treat it as, it's just sort of shifting what the 0 of your potential energy is. What about kinetic energy? The kinetic energy, because this is a rigid body, we'll have 1/2 m the magnitude of the inertial velocity plus 1/2 IG, the magnitude of the angular velocity squared. So this this ends up being 1/2 ms dot squared. Now we need to figure out what IG is. IG, let's assume we have a disk. So if you could look it up in a table for a disk that has a certain radius. What did I say? The radius. I'm going to use capital R. No, am I? Yeah, why not? Capital R. We have IG is 1/2. So about that axis, 1/2 mr squared. So we get over here 1/4 mr squared theta dot squared. That's the kinetic energy. Now put them together. This is the unconstrained Lagrangian. We have 1/2 ms dot squared plus 1/4 mr squared theta dot squared. Minus of a minus. So this becomes plus mgs sine alpha. This is our unconstrained Lagrangian, meaning we haven't yet imposed the constraint. The main constraint is the rolling without slipping. So that's good. All right. The rolling without slipping constraint, and I think we mentioned this in an earlier one. Instead of s, we use x, but we've got s dot equals r theta dot. But we want to write this in the form of something equals 0. So just move these around. So this is s dot minus r theta dot equals 0. And notice that this is in the form, it's q1 dot plus something times q2 dot equals 0. So it's in the appropriate linear non-holonomic form or Pfaffian form. So we only have one constraint, so A1s is 1. A1 theta is negative r. And then if you want A1t is 0. It's just not there. Okay. So Lagrange's equations are d dt partial L partial s dot minus partial L partial s equals lambda 1 A1 s. I guess we could write this way as well. We'll write this as CS, where CS is lambda 1 A1s. And we've already computed up here what CS is in terms of force of constraint and moments of constraint, and same for C theta. So we've got two Lagrange's equations. D by dt partial L partial theta dot minus partial L partial theta equals C theta, where C theta is lambda 1 A1 theta. And we've got what these things are over here. So those are our Lagrange's equations. Maybe I'll highlight with purple outline. We've got three equations. The purple things. and 3 unknowns, which are S double dot, theta double dot, and lambda 1, the one Lagrange multiplier. So we can find from these equations and unknowns, and maybe I'll leave it as an exercise, you can find that theta double dot, oh, sorry, the S double dot. You can find that S double dot equals 2/3 G sine alpha for this case. So that's cool. And then from this equation itself, you could figure out how theta double dot and S double dot are related because they're just proportional to each other. So this is equal to 2/3 G over R sine alpha. All right. So you can also find lambda 1. And lambda 1 is negative 1/3 mg sine alpha. So CS, saying that this is lambda 1 A1S, is negative 1/3 mg sine alpha. We'll call that equation 1. C theta is lambda 1 A1 theta, which is 1/3 mgr, sine alpha, call that equation 2. And if we compare these equations with what we wrote up above for the relationship between the Newtonian forces and Newtonian moments, so comparing 1 and 2 with the equations relating with the force of constraint and moment of constraint, we can find something. We can find that the force of constraint is equal to negative 1/3 mg sine alpha in the E1 direction. That's parallel to the ramp. We'll sketch this, and at the moment of constraint is equal to negative R 1/3 mg sine alpha in the E3 direction. Okay, so if we want to sketch the situation and see if things are matching up for forces and moments of constraint. So here is our center of mass for our disk. And this is saying that the force of constraint, and where's it being applied? Well, it's reasonable to think of it being applied at the point of contact, because that's the only place where this rigid body is contacting anything else. So we could sketch the force of constraint there. And remember our directions. This is E1, this is E2, and then E3 coming out of the screen. So this says the force, as this is going downhill, the force of constraint is in the negative E1 direction. So it's resisting. And we have a moment. The moment of constraint is in the negative E3 direction. So I guess we could just draw it that way. Is there another way that we can interpret what the moment of constraint is? Well, yes. if we were to write, the moment of constraint is probably due to the force of constraint. So if we write the location, this is the location of point P, with respect to G, then we could write the moment of constraint is location where the force is applied, the moment arm, cross the force of constraint. And does that work out? We use the right-hand rule, R cross F. I've got something pointing in the negative E3 direction, so it seems to match up. So the force of constraint is F constraint is a tangent to the ramp at the contact point. And the resulting moment is the moment of constraint. Right. So they're not independent of each other. They're related to each other in what seems like a straightforward way. Okay. And why are these forces here? We've sort of imposed, this thing is rolling without slipping, which is something that we observe. And underneath it all, the forces and moments that are making that happen are these forces and moments of constraint. So these are that's what these are. These are the forces and moments necessary to keep the disk rolling without slipping. So that's cool. I guess maybe I didn't say, hopefully it was clear to you what RPG is. I forgot to put this. RPG, it's R, but then it's in the negative E2 direction. So that's why you pick up this R right there. Okay. All right. For this, I assumed a disk. And for a disk, I got a certain acceleration up here, this yellow highlighted equation. What if I didn't use a disk? This we're gonna end on this. This if I can do this, we will have a downhill race of two objects: a hollow cylinder, like a hollow cylinder. It's made of metal, but it's kind of the same shape as if you were to get packing tape. And then this is solid cylinder. You've got the same radius to machining precision. Okay, so let's do a downhill race. So what if a disk wasn't used? Something else that would change. That would change what? That would change. Wouldn't change. Suppose they have the same mass. We would be changing the moment of inertia. So if we have, I want to call this a downhill race. So T, U is the same for each. The potential energy due to gravity, right? It's going to be the same thing, negative mg s sine alpha for things that are going downhill. So whether it's a hollow cylinder or a filled cylinder, solid cylinder. if they've got the same radius, the everything's the same except the moment of inertia. So T equals 1/2 m s dot squared, just like above, plus 1/2 IG theta dot squared. So here's IG. You could look at up the moment of inertia for various objects. Well, I mean, I guess before we go, I could just, before we do the race, just looking at them, I don't know, do you have an idea of which one's gonna, if they're released from rest, which one will make it downhill first? And you could put it in the comments if you have. You want to guess? You say hollow cylinder, solid cylinder. So for a solid cylinder, and you could just look this up, that moment of inertia about its axis of symmetry, it's 1/2 mr squared, just like a disk. Okay, for the hollow cylinder, this is just mr squared. There's no factor of 1/2. If we treat both of these as just, we're writing them as k, some non-dimensional number times mr squared, then this one has k equals 1/2. This one has k equals 1. Okay. So we could write the kinetic energy as using the fact that this is rolling without slipping. So theta dot equals s dot over r. We'll just rewrite it that way. Put it in the kinetic energy already, 1/2 m s dot squared plus 1/2 ig 1 over r squared s dot squared. But now put in ig equals kmr squared. So this becomes 1/2 m s dot squared times 1 plus k. And now using L equals T minus U, we get that S double dot from Lagrange's equations is equal to 1 over 1 plus K G sine alpha. So what is our prediction based on this? If we lower the denominator here, then we'll have a larger S double dot. So lowering the denominator means smaller k. Smaller k implies higher acceleration. So this would predict that the solid cylinder should win. So let's try it. I've got a ramp here, red ramp, and I've got a solid cylinder and a hollow cylinder. And I will try to release them both at the same time as best I can. And we'll see which one gets to the end of this first. Ready? And it's the solid cylinder. So the solid cylinder is the one in the back here. So here we go. Again, see it coming up ahead. So solid cylinder wins. Now, there is something to notice about what I did here for this downhill race part. In this downhill race, I just directly substituted in, because it could also be written as a holonomic constraint, as in theta equals s over r. Because we could write the holonomic constraint, I can just directly substitute in wherever I have theta. I put in S. So I could write this Lagrangian completely in terms of S and S dot, right? Because U is a function of S, kinetic energy is just a function of S. So for this downhill race, I skipped all the stuff with having two generalized coordinates and solving for the Lagrange multiplier because it quickly gives me an answer. I did the exercise above where I had more generalized coordinates than necessary, and then also had to solve for the forces of constraint and the Lagrange multiplier along the way. That was just to illustrate how to get the force and moment of constraint. So we'll end there and then talk about other topics next time.